Hello everyone, welcome to module 5. So in this module we're going to talk about equilibrium and the extent of chemical reactions. So in this module we're going to talk about the equilibrium state and the equilibrium constant, the reaction quotient and the equilibrium constant. Next we talk about expressing equilibrium in terms of pressure, so with using Kc and Kp terms, so which is equilibrium constant is equilibrium constant for concentration and pressure equilibrium constant. So next you have comparing a reaction quotient and equilibrium constant to determine the reaction direction, and finally how to solve equilibrium problems, and end the entire lecture with the reaction condition as the equilibrium by discussing the Le Chatelier's principle. So let's start with the equilibrium state. So what is an equilibrium state? So all reactions in general are reversible, and under suitable conditions they generally reach a state of equilibrium. So what does equilibrium basically mean is that the concentration of the product and the reactants no longer change because the rate of forward and the reverse reactions are equal. This is an important point to remember. At equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. Now, chemical equilibrium is much more of a dynamic state because the reactions continue to occur, but because they occur at the same rate, no net change is observed on the macroscopic level. It doesn't mean that at equilibrium there's no reactions completely. It's more of a dynamic state where, for example, the reactant forms product, and then again in the opposite direction you have a product forming the reactant back again. So the net change here when you combine the two reactions is zero. So this is the term equilibrium. This is what chemical equilibrium refers to. So let's take the example of let's say N2O4 decomposing to form 2NO2. And you notice that the reaction initially has mostly a colorless N2O4, and as the reaction proceeds you start noticing that there is much more formation of NO2. NO2 has a little more reddish brownish color, so the mixture starts turning brownish, and as you reach a certain point, even if the time increases, there is no change in the amount of color change that happens to the gas. This point is generally called as the equilibrium point. So this is generally called as the equilibrium point, and that is the point where the gas generally does not have any further formation into the product. Even though there are reactions happening, notice that there are reactions happening, but the reactions do not yield anything specific there. So that is one of the reasons what we talk about equilibrium. So now let's come to the concept of equilibrium constant. So what is an equilibrium constant? So we discussed the reaction N2O4. So let's consider the reaction. N2O4 gives 2NO2. Now notice that we told that the rate of forward reaction is equal to the rate of reverse reaction at equilibrium. Now at equilibrium we know that the coefficient itself becomes the exponents. So we can write that K forward times N2O4 to the power 1 equals K reverse times the NO2 here. So notice that here we are only taking the reactant. So in the reverse reaction, NO2 becomes the reactant. So NO2 to the power 2. So notice that we are using that exponent directly. Why are we using that exponent there, coefficient there? Because that represents the actual value of the reaction right here. Now we have the values right here. Now next thing we have to understand is, let's consider that we write K forward by K reverse. So which means that we are bringing this here and we are pushing this to the other side. So this gives you NO2 to the power 2 and over N2O4 concentration. So this ratio of the rate of forward reaction over the rate of reverse reaction is called as the equilibrium constant K. So K forward by K reverse. So this K is called as the equilibrium constant. So K here is called as the equilibrium constant, and from this we can write that K is equal to NO2 to the square over N2O4. So this is how we write the equilibrium constant for a given reaction like this. So to simply understand what K represents here, so K and let's talk about the extent of reaction. So generally K does not represent the rate of reaction. K is actually a more of a quantity that represents the amount of the extent to which a reaction can occur. So K reflects a particular ratio of product concentrations to the reactant concentrations for a reaction. So it therefore indicates the extent of reaction. Extent represents that how far a reaction proceeds towards the product at any given temperature, which means that how much is the product that is going to be produced is the representation by K. So a small value of K generally indicates that the reaction will yield a little amount of product before reaching equilibrium. So which means that when you have a small value of K, the reaction generally favors the reactants. Now, when you have a large value of K, it indicates that the reaction reaches equilibrium with very little reactant remaining. So which means that the reaction here favors the product formation. So let's take an example here. Notice that here this is the reactant and this is the product. There is only one product formed, so we can write K here. Let's consider there are a total of 50 of them, so 1 over 49. This represents that it only does not favor the products, but it favors the reactants. Now let's take another reaction where you have reactant and product here. Now there is more product in consideration with the reactant. So at this equilibrium, now we can write that the reaction favors the product. Now here we have equality, so which means that it does not favor both of them. It favors it comes in the middle of them. So next, let's consider what we call the reaction quotient. So reaction quotient is generally determined by. So let's consider if you have a reaction AA plus BB gives CC plus DD. So the reaction quotient Q is given as C to the power C, D to the power D over A to the power A times B to the power B. So this is the reaction quotient QC. Now what does QC represent here is that at equilibrium, so basically what will happen here, QC becomes K. This is an important point to remember, that the reaction quotient is a general quantity that represents the progress of reaction. Now at equilibrium, the reaction quotient equals to the equilibrium constant. So Q generally gives the ratio of product concentrations to the reactant concentrations at any point in a given reaction. So for a particular system and temperature, the same equilibrium state is attained regardless of the starting concentrations. So the value of Q here generally indicates how close the reaction is to the equilibrium and in which direction it must proceed to reach the equilibrium, whether it's going to proceed towards the reactant or the product. So what happens during the reaction? So during the reaction, Q continuously changes and Q is never equal to K. Now once it reaches the equilibrium point, so at some point in time it reaches the equilibrium point, Q becomes equal to K and the concentration of the reactant and product will stay constant for the further part of the reaction. So this here is the idea behind Q. Now let's take the initial example here. So the initial and equilibrium concentration ratios for N2O4 NO2 system at 200 degrees centigrade. You start with a Q of 0. So as you start noticing that there is an increase in the NO2 concentration, notice that there is a decrease in the N2O4 concentration and then an increase in the, there is a decrease in the NO2 concentration and there is an increase in the N2O4 concentration. You start noticing that Q starts increasing and Q reaches a particular value where the value stays constant throughout the entirety of the rest of the reaction. So this here, once it achieves that value itself becomes the equilibrium constant. And the concentrations at that equilibrium value are called as the equilibrium concentrations. So let's take an example of these problems right here. So what is given here? So write the quotient, reaction quotient for each of the following reactions. So let me copy these square. So these are the ones that are given right here. So first for A, what would be QC right now? So QC again is starts with the product concentration. So NO2, there is no coefficient there, times O2 over the concentration of N2O4. For B, you have QC becomes concentration of NaOH times the concentration of H2 over the concentration of Na times the concentration of H2. Now this is the question, what should be included in the quotient of the concentration here? Now the idea here is to first check the balance of the equations right here. So always remember that we always have to check the balance of the equations. Notice that in the first equation we have N2O5 becoming NO2 plus O2. So first thing you'll notice is that it's not balanced, so we cannot write QC right away. So first write the balanced form of the equation. So for A right here, you have N2O5 gives NO2 plus O2. So from this we can write, let's say for example 2NO2. That will give you 2 nitrogens on this side and 2 nitrogens on this side. And you have 4 nitrogens and 6 nitrogens. Let's consider that we have 2 N2O5. So that means that here we have 4 nitrogens. So we have 4 NO2. So you have 4 nitrogens, and you have 8 oxygen plus 2 oxygen, 10 oxygen. So that's 10 oxygen. So this is the balanced form of the equation. Now try to write the QC value. Now remember that in QC, when writing QC, we only write the ones that are in the form either as a gas or we are either in the aqueous form. We do not write the quantities that are either a solid or a liquid. So we do not write these in the QC, in the reaction quotient formula. So we do not include those quantities because those quantities do not undergo any change in the concentration. The only things that undergo change in the concentration are the ones that are either gaseous or aqueous. So which means that they are either a gas or a solution. So only those are the ones that undergo any change. Now let's write QC here. Again, product concentration, which is NO2 to the power 4 times O2 over N2O5 square. Next, B. Let's try and balance the equation first. You have Na solid plus H2O liquid gives NaOH plus H2. Now notice that you have 3 hydrogens right here, and there's only 2 hydrogens on this side. So which means that let's consider there is 2 H2O. So which means we have 2 NaOH. So which means 2 Na here. So that gives you 2 oxygens and 2 hydrogens. So 2 oxygens and 2 hydrogens plus 2 hydrogens. So that's a total of 4 hydrogens and 2 oxygens. So that's balanced. So the reaction is balanced. Now notice that here, this is a solid and this is a liquid, while the other 2 are gaseous. So one is aqueous, the other is gaseous. So which means that these 2 are excluded from the formula. So QC becomes NaOH power 2 times H2. That's it. So we do not write the denominator. The main reason is because on this side you have solid and liquid. Now whenever you have solid and liquid, exclude them from the reaction quotient formula. So use the same principle now and try to balance the equation C first, and then second try to write down the reaction quotient for that particular value. So pause the video right here and try to solve that problem. Next, let's talk about the forms of the equilibrium constant and the reaction quotient. So when you have for an overall reaction, that is the sum of 2 or more individual reactions, the Q overall is given by the product of Q1 times Q2 times Q3 and so on. K overall is also given by the product of K1 times K2 times K3 and so on. Now another one to remember is the direction. So the direction can be more of a reverse quantity. So the coefficient, reaction quotient reverse is 1 over the reaction quotient forward, and equilibrium constant reverse is 1 over equilibrium constant forward. Next, if you have a quotient of a balanced reaction that are multiplied by a common factor, so which means that if Q dash is given as Q to the power n, so we can write that it is the concentrations whole to the power n. The same thing with K dash, which can be written as K to the power n, which then also becomes the same value. So let's take an example of this problem right here. So you have nitrogen dioxide is a toxic pollutant that contributes to the photochemical smog. One way it forms is through the following sequence. First you have nitrogen plus oxygen forming 2NO, and 2NO plus O2 forming 2NO2. Now what is given here? Show the overall QC for this reaction sequence is the same as the product of QCs of the individual reactions. And finally, given the both reactions occur at the same temperature, find Kc for the overall reaction. So they have given Kc1 and Kc2. So let's try and find the reaction. So first things first, always write down the individual reactions first. So N2 gas plus O2 gas forms 2NO gas. Next you have 2NO gas plus O2 gas forms 2NO2, which is also a gas. So they have given Kc1 and Kc2. So Kc1 value is 4.3 times 10 to the power negative 25, and Kc2 is 6.4 times 10 to the power 9. So notice that you have two reactions now. First, find the overall reaction. So the overall reaction is add the products and add the products and the reactants. So you have N2 plus O2 plus 2NO plus O2 gives 2NO plus 2NO2. So 2NO, 2NO gone. So we can write that N2 plus 2O2 gives 2NO2. So this is the overall reaction. First, let's find QC1, which is the reaction quotient for the first reaction. So which is going to be, so let's find Q1 first. So Q1, again, the first reaction only. So which becomes the product is NO2 square by concentration of N2 times concentration of O2. And you have Q2, which is going to be, the product is NO2 square over NO square times O2. Now what is Q overall for this reaction? So for this reaction it becomes NO2 square over N2 times O2 square. So first thing that we need to do is, we know that to actually write the value, which means we have to find Q1 times Q2, if that is true. So what is Q1 given as? So you have NO square over N2 times O2 times NO2 square by NO square times O2. So NO square get cancelled. You get NO2 square over N2 times O2 becomes O2 square. Now notice that this value exactly is the same as Q overall. So we can write that this is true. So this actually works. So if this works, so we know that K overall becomes K1 times, so Kc1 times Kc2, so Kc overall. Now K overall, the values are given as 4.3 times 10 to the power negative 25 and 6.4 times 10 to the power 9. So multiply both the values. So that gives you a final answer of 2.8 times 10 to the power negative 15. So this is the Kc overall value, the equilibrium constant for the combined reaction. So this is how you can solve the problem. Next, let's try to solve another problem. So for the ammonia formation reaction, the reference equation is N2 plus 3H2 gives you NH3, 2NH3. Kc is 2.4 times 10 to the power negative 3 at 1000 Kelvin. What are the values for Kc for the following balanced equations? So now notice that they are manipulating the equation based on the values that are present there. So first, let's try and calculate the first one. So first one is given as 1 by 3 N2 plus H2 gives 2 by 3 NH3, and the reference equation is N2 plus 3H2 gives 2NH3. So from this we can write Kc originally as NH3 square over N2 times H2 to the power 3. So from this you notice that when you take the common quantity out, so what is the common quantity in all of these quantities is 1 over 3 times N2 plus, so this becomes 3H2 gives 2NH3. So notice that the value that is being multiplied is 1 over 3. So when you write Kc for this equation, that becomes NH3 to the power 2 by 3 over N2 to the power 1 by 3 times H2. Now notice that we need the K dash value. So let's try to find K dash over Kc. K dash is NH3 2 by 3 by N2 to the power 1 by 3 times H2 over NH3 square over N2 times H2 cube. Now, so we know we need K dash by Kc. So notice that now we can take reciprocal values. So which means that NH3 to the power 2 by 3 by NH3 square times, so when you reciprocal these values, so these two will go upwards. So which means that N2 over N2 to the power 1 by 3, and you have H3 H2 cube by H2. Now notice that the value that is being multiplied here is 1 by 3. So 1 by 3 is the value that's being multiplied here. So we can take that one specifically as the main value. So rather than doing this, we can consider that the equation is multiplied with 1 by 3. So which means that we know that K dash is K to the power n. So K to the power n here, n value is 1 over 3, K to the power 1 by 3. So the original value of K that is given here is 2.4 times 10 to the power negative 3. So we can write 2.4 times 10 to the power negative 3 to the power 1 by 3. So from this we can write that the value calculated the value, so that gives you 0.13. So K dash for this reaction is 0.13. Now let's go to the second problem. So in the second problem, so first things first to remember here is that they have reversed the reaction. So first we have to reverse the reaction, and then they've also multiplied 1 by 2 to the reaction. So K dash for the second reaction becomes 1 by K C, and to the power they've also multiplied 1 by 2. So which means to the power 1 by 2. So 1 over Kc to the power 1 by 2. So that becomes 1 over 2.4 times 10 to the power negative 3 to the power 1 by 2. So that gives you a value of 20. So K dash becomes 20 for the reaction B. So first remember that first things first, they have reversed it. So which means that the original value becomes K dash becomes 1 by Kc, and then they multiplied a power 1 by 2 to that. So we give the power 1 by 2 to the whole value. So which gives you the final answer of K dash. So that is how we solve problems involving different values of K. Next, let's talk about K and Q for heterogeneous equilibrium. So heterogeneous equilibrium involves reactants or products in different phases. For example, you have CaCO3 in solid phase gives you CaCO in solid phase times plus CO2. Now a pure solid or liquid always has the same concentration. This is an important point to remember, is that a pure solid or a liquid will always have the same concentration. Now the same number of moles per liter or solid or a liquid. Now the expressions for Q and K only include the species whose concentrations change, which means that we include both the aqueous solutions as well as gases. So which means that we omit pure solids and pure liquids from the expression for Q and K. So for this equation right here, we take out CaCO3 and CaO, only writing the Q value for CO2. So which means that the solid concentrations do not change, but the gas concentration does change. That's the idea behind the writing the equation right here. So this is a table that shows you the reference equations for all the formulas that we used until now. So make sure that you take a look at this and review this particular formulas. Next, let's go to the expressing the equilibrium with pressure terms. So we used until now the concentration terms, and we can also use the same terms in terms of pressure. For example, in this reaction right here, rather than writing the concentration, so QC would be written as NO2 square over NO square times O2. But when we write QP, the same thing happens, but rather than writing the concentration term, we write the pressure term. So we write PO2 square by the pressure of NO square times the pressure of O2. So this becomes the QP term. Now, how would we calculate Kp? So Kp value is generally given by the formula Kc times RT to the power delta N of the gas, so which is the change in the number of moles of the gas. Now, most commonly, the amount of gas does not change in a reaction, so which means that delta N of a gas is generally equal to 0, so which means that Kp value equals to Kc. So Kp value becomes equal to Kc. So let's take an example problem right here. A chemical engineer injects limestone into hot flue gas of a coal burning power plant to form lime, which scrubs SO2 from the gas and forms gypsum, which is CaSO4 taken, so 2H2O. Find Kc for the following reaction if CO2 pressure is in atmosphere. So this is the value right here that is given right here. So CaCO3 gives CaO plus CO2 and the value for Kp is given. Now, what is happening in terms of the change in number of moles of the gas right here? Now, how would you calculate the delta N of the gas? So let's take into consideration the actual formula itself. So we have CaCO3, which is the solid, gives CaO, which is a solid, plus CO2, which is a gas. Now this is the question right here. How would you calculate delta N of the gas? So we have to calculate the number of gaseous products minus the number of gaseous reactants. The number of gaseous products right here is 1. The number of gaseous reactants is 0. So which means delta N of the gas is 1. So the formula gives you Kp. The Kp value is 2.1 times 10 to the power negative 4 at a temperature of 1000 Kelvin. So we know that the R value is generally written in terms of atmosphere, so which is 0.0821 atmosphere liter per mole Kelvin. Now we need to find Kc. So we know that the formula for Kp is Kc times RT to the power delta N of the gas. So we need to find Kc right here, so which becomes Kp over Kc times RT to the power, so it becomes RT to the power delta N of the gas. So Kp value is given here, so which is 2.1 times 10 to the power negative 4 over R here is 0.0821 times the temperature is 1000 to the power 1. So when you calculate this final value, that value gives you 2.6 times 10 to the power negative 6. So this is the value for Kc. So these are the ones that we generally use. So whenever you calculate the number of moles of gas, we calculate the number of gaseous products minus the number of gaseous reactants. So most commonly it's 0, but there are cases where you might end up getting more than that. Let's talk about the value of Q that indicates the direction in which an equilibrium might proceed. So because Q and K values are really good in determining the direction of the reaction, so we use three main conditions: Q less than K, Q greater than K, and Q is equal to K. So when Q is less than K, the reactants generally must decrease and the products will increase. The reaction will proceed towards the products, so which means that the reactant to product until the equilibrium is achieved. So which means that it proceeds towards the products until the equilibrium is achieved. Now when Q is greater than K, the reactant must increase and the product will decrease. So the resulting in the reaction proceeding towards the reactants until the equilibrium is reached. So the products will start forming reactants. Now when Q is equal to K, this is the point where we generally use mainly. The system generally is at equilibrium and there is no further net change that takes place. So this is how we determine the direction of reaction. Now if Q is less than K, there is an increase in the product. If Q is greater than K, there is a decrease in the product and increase in the reactant. So, and finally, both conditions will always try to achieve the equilibrium condition, which is Q is equal to K. So let's try and solve this problem. So what is given here? For the reaction A to G, the equilibrium mixture at 175 degrees centigrade is the concentration of A is given and the concentration of B is given. So these are the equilibrium concentrations. So first from that we can calculate Kc, so which is the equilibrium constant of B over the equilibrium constant of A. So the equilibrium constant of B is 1.2 times 10 to the power negative 4 over the equilibrium constant of A is 2.8 times 10 to the power negative 4. So when you calculate that, you get a value of 0.43. Now, first things first, we have to remember is that here A is red and B is blue. So that is the given here. And they have given us 4 situations and they're asking us to calculate Q, and they're asking you to calculate does the reaction progress to the right or left or not at all for all of these mixtures in each of these reactions. So we have to basically calculate Q based on the values that are given. So based on the number of blues and the number of red. Remember that blue is the product by the red. So number of blues by the number of red. So the number of blues here, you have 1, 2, 3, 4, 5, 6, 7, 8. 8 blues over 2 reds. So Q1 becomes 8 over 2, which is 4. Next, let's calculate Q2. You have 1, 2, 3. So 3 blues. And you have 1, 2, 3, 4, 5, 6, 7 reds. So 3 over 7. Next, we have Q3, which is going to be number of blues, which is 1, 2, 3, 4 over number of reds, that is 1, 2, 3, 4, 5, 6. So 4 over 6. Next, you have Q4, which is the number of blues, which is again 1, 2 over reds, 1, 2, 3, 4, 5, 6, 7, 8. 8. So from this, we have the Q1 value, which is 4. Q2, which is 3 over 7. And Q3, which is 4 over 6. And Q4, the value is 2 over 8. So which can be written as 1 over 4, which is 2.5. 4 over 6 is 2 over 3, that is 0.66. And 3 over 7 is 0.43. And Q1 is 4. So the first condition is Q1 and K. So notice that Q1 is 4 and Kc is 0.43. So we can write that Q1 is greater than Kc. So when Q is greater than K, what will happen to the reaction now? So the reaction proceed to the left. So which means that they are going towards the reactants. Next, you have Q2, which is equal to Kc. So which means that the reaction is at equilibrium. Right? And you have Q3, which is also greater than Kc, which means that again the reaction proceeds to the left towards the reactants. Next, last we have Q4, which is less than Kc. So which means that here the reaction proceeds to the right. So whenever you see the term left, it's reactants. When towards the right, it is towards products. So this is how we can use Q and K relationship and the values to determine the direction in which the reaction will proceed. Next, let's try another example. For a reaction, N2O4 gives N2N2, 2NO2. You have Kc at 0.21 at 100 degrees centigrade. At a point during the reaction, N2O4 is 0.12 m and NO2 is 0.55 m. Is the reaction at equilibrium? If not, which direction is it progressing? Again, first things first, at any given point, if they have given it, which means that the QC is going to be product by the reactant. Now, the product concentration at a given point of time is given as 0.55 square divided by NO2. So N2O4 is 0.12. So QC value will become 2.5. Now, given Kc value is 0.21. So we know that QC is greater than K. So when it is greater than K, the reaction proceeds towards the left, which means that it is going to proceeds to the left towards the reactants. So the reactant here is N2O4, so which means that it proceeds towards the N2O4 formation. So it means that here N2O4 concentration will increase while NO2 concentration will decrease at that point of time. So that is how we can write the reaction. Next, let's take a look at how to solve equilibrium problems. Now, if equilibrium quantities are given, we generally substitute them into the expression for Kc to calculate its value. Now, if only some equilibrium quantities are given, we generally use what we call as the reaction table to calculate them and find the equilibrium constant. Now, what does the equilibrium reaction table generally show? First, it shows the balanced equation. Second, it shows the initial quantities of reactants and products. Third, it shows the changes in these quantities during the reaction. And finally, it shows you the equilibrium quantities. So this is an example problem. So we are going to discuss this example problem in the next lecture. I will see you again in the next.